Some machines built in antiquity are still working perfectly today. This video reveals the secrets of ancient machines that worked beyond their time, giving you a new understanding of human ingenuity. We will explore complex astronomical calculators that predicted eclipses for centuries and water clocks that kept time for generations. What does the incredible endurance of these devices tell us about knowledge that was lost to history? How much of our modern world is built on foundations we have forgotten? The rhythmic drip of water echoing in a quiet chamber, the steady turn of a stone gear under starlight, these were the heartbeats of ancient machines. In workshops lit by fire, master craftsmen shaped bronze and stone with nothing but hand tools and profound patience. Their creations were not crude prototypes, but the pinnacle of technology for their age, intricate devices designed to solve real-world problems. These are what we define as ancient machines, mechanical wonders built before the age of industry, harnessing fundamental forces like water pressure, geared motion, and celestial mechanics. Historians of technology see them as the ultimate fusion of art and science, where every component served a purpose. Consider the great water clocks of the ancient world. These were not mere timepieces but civic engines, using the predictable flow of liquid through precisely calibrated channels to mark the hours for an entire city. This required a sophisticated, almost intuitive grasp of fluid dynamics, principles we would later codify with complex mathematics. The very materials chosen, bronze that resisted corrosion and stone that withstood the elements, speak to a deliberate intention for longevity. So what does it truly mean for a machine to work beyond its time? It is more than simple durability. It is a continued performance of its original function, a voice from the past that still speaks with precision. This enduring operation challenges our modern assumption that newer always means better, forcing us to reconsider the depth of knowledge that was somehow lost, forgotten, or overlooked for centuries. From the quiet pulse of a water clock, we journey to the depths of the sea. In 1901, a sponge diver near the Greek island of Antikythera surfaced with a puzzling find, a corroded lump of bronze and wood retrieved from an ancient shipwreck. It seemed like just another piece of debris, yet this unassuming object would eventually be recognized as one of the most astonishing artifacts ever discovered, the Antikythera mechanism. Decades of painstaking research, led by pioneers like Derek de Solla Price, revealed it to be a sophisticated analog computer, a device of breathtaking complexity from a time we assumed was dominated by simpler tools. Crafted around 100 years before the Common Era, its purpose was written in the stars, designed to predict the movements of the sun, the moon, and the known planets with a precision that would not be rivaled for over 1,000 years. Imagine holding a compact wooden case no larger than a shoebox, within which more than 30 interlocking bronze gears worked in perfect harmony. This was not a simple calendar, it was a mechanical model of the cosmos. By turning a hand crank, an ancient user could advance time forward or backward, watching as pointers on dials displayed lunar phases, predicted solar eclipses, and even tracked the cycle of the ancient Olympic Games. Each precisely cut tooth on each tiny gear represented a deep understanding of celestial cycles, a knowledge of mathematics and engineering that seems to defy its era. The very fact that it survived 2 millennia submerged in salt water is a miracle in itself, but its existence poses a far greater question than how it endured. How did ancient Greek artisans achieve such precision machining without the tools we consider essential? The gears were not crude approximations. They were carefully calculated, with tooth counts that correspond to specific astronomical ratios. This was not a one-off curiosity. It was the product of a highly developed technological culture, a tradition of craftsmanship and scientific inquiry that history barely recorded. So why was this knowledge lost to the ages? The mechanism stands as a silent witness to a level of technological sophistication that faded from memory, only to be rediscovered by accident. Its intricate workings challenge our linear view of progress, suggesting that peaks of human ingenuity can arise, be forgotten, and then be found again, waiting for us to understand their secrets. The steady drip of water marking the hours was the pulse of an ancient city, a rhythm built not on gears but on gravity itself. These water clocks, known as clepsydræ, were far more than simple timers. They were masterpieces of hydraulic engineering that governed daily life for centuries. From the sun-baked courtyards of Egypt to the philosophical schools of Greece and the imperial courts of China, civilizations independently converged on the same elegant solution, using the unerring flow of water to measure the passage of time. The principle was brilliantly straightforward. Water would trickle at a constant rate from a primary reservoir into a receiving vessel, where a rising float or a marked scale would indicate the hour. But the most advanced versions were marvels of complexity, featuring automated figures that struck bells, miniature theatrical scenes that unfolded on the hour, and intricate systems of gears powered solely by the water's movement. Historical records speak of clocks that not only told time but also displayed the movements of celestial bodies, creating a dynamic model of the heavens driven by nothing but liquid and ingenuity. The true testament to their design, however, was their incredible lifespan. The Tower of the Winds in Athens, for instance, housed a public water clock that functioned for more than 200 years. Its stone construction and connection to a reliable spring allowed it to guide everything from market openings to religious ceremonies, outliving the very civilization that built it. This longevity was no accident. It was the result of robust, sustainable engineering, using durable materials like stone and bronze, and principles so fundamentally sound they required minimal intervention. What can these ancient timekeepers teach us today? In an age of complex electronics and planned obsolescence, their centuries of service remind us of the profound power of simple, elegant design built to last. They show that true technological sophistication is not always about adding more complexity, but about perfecting a core principle to its most resilient form. This pursuit of perfect timekeeping, however, would find an even more astonishing expression in a device lost at the bottom of the sea for 2,000 years. While the Antikythera mechanism calculated the cosmos with gears, another form of ancient genius was etched in stone, designed to track the heavens across millennia. These were the great astronomical calendars, built not in workshops but into the landscape itself, achieving a perpetual accuracy that defies simple explanation. Ancient priests and sky watchers used stone alignments, towering pyramids, and precisely carved wheels to monitor celestial cycles with a precision that can rival even modern instruments. From the monolithic rings of Stonehenge on the English plain to the intricate observatories of the Maya in Central America, these structures were not just monuments, they were massive, permanent machines for reading the sky. They harnessed the most reliable power source imaginable, the predictable motion of the Earth, Sun, and stars, and they were built from materials meant to last forever. The Mayan calendar system, for instance, was a breathtaking intellectual achievement. Without telescopes or advanced optics, Mayan astronomers accurately calculated the 584-day cycle of Venus, a feat of observational data and mathematics so precise it persisted through generations of cultural change. Their complex calendar rounds were carved into stone stelae, preserving their functionality long after the civilization itself transformed. In Egypt, the Dendera zodiac, a beautiful bas-relief carving on a temple ceiling, still maps the stars and aligns with specific celestial events to this day. Why would ancient societies invest such immense resources into tracking the sky over the long term? For them, it was a matter of survival and sovereignty. Predicting the solstices meant knowing when to plant and harvest. Forecasting planetary movements was tied to the legitimacy of rulers and the favor of the gods. This was a science deeply woven into the fabric of their culture, a way of imposing order on a vast and sometimes unpredictable universe. Their success, achieved with stone and patient observation, offers a humbling lesson for modern astronomy. It reminds us that the foundation of our science is not just technology, but the enduring human drive to understand our place in the cosmos, a quest that began with standing stones casting long shadows on the dawn of the solstice. This profound understanding of natural rhythms would soon find expression in a more personal and portable form of ancient engineering. The quiet, relentless mesh of bronze gears is a sound that once echoed through the ancient world, a testament to a mechanical genius built to last. We find these intricate gear systems at the heart of history's most resilient machines, from the monumental Roman water mills to the legendary automata of Greek legend. They were not simple components, but the product of a sophisticated understanding of physics and material science. Ancient engineers selected metals like brass and wrought iron not just for their strength, but for their ability to resist wear over countless cycles of motion. Each gear was painstakingly shaped, its teeth filed and balanced to ensure smooth engagement, reducing friction and the gradual grinding down that would otherwise doom a lesser mechanism. The Barbagal water mill complex in southern France stands as a powerful example, a sprawling industrial site where 16 separate water wheels, connected by a series of robust gear trains, ground enough flour to feed the entire city of Arelate for centuries. This was not a delicate prototype, it was a powerhouse of relentless, daily operation. Its longevity was no happy accident. Builders employed clever lubrication techniques, using rendered animal fats to keep the gears turning smoothly, and they strategically placed their machinery to protect it from the elements and to utilize the most consistent water flow. How did they achieve such precision without digital calipers or computer modeling? The answer lies in a master-apprentice tradition of knowledge, where skills were passed down through generations, and in the use of templates and jigs that allowed for the replication of perfectly shaped components. The true lesson for modern mechanics is not in the tools they used, but in their philosophy of design, building for function and endurance over speed and disposability. This mastery of gearing to create reliable, long-lasting power would soon be directed toward an even more ambitious goal, the creation of lifelike machines that seem to possess a will of their own. A statue in a sun-drenched temple courtyard moves, its arm rising to pour a ceremonial offering before returning to stillness. For generations, this sight would repeat day after day, powered not by a priest but by a hidden machine. These were the automata of the ancient world, self-operating devices that blurred the line between divine miracle and human engineering. From the steam-powered wonders of Hero of Alexandria to the legendary south-pointing chariots of China, these creations were designed for a single purpose: to perform a specific, repetitive action indefinitely. Their operation relied on fundamental forces, the steady descent of a weight, the relentless flow of water, or the controlled expansion of heated air. This was not magic, it was mechanical ingenuity built to last. Historical texts describe temple doors that opened automatically as a fire was lit on the altar, a clever system of ropes and counterweights driven by the heat and pressure of expanding air. The awe this inspired in worshippers was part of the design, a demonstration of a community's sophistication and their direct connection to the powers they revered. Why would ancient societies invest so much effort into machines that performed such simple tasks? The answer lies in the profound cultural value of reliability and spectacle. An automaton that never tired, that performed its duty for decades, was a symbol of eternal order, a mechanical heartbeat within a sacred space. The very longevity of these devices, some functioning for a century or more, was a direct result of their elegant simplicity. A mechanism designed to turn a figure on a wheel, driven by water dripping at a constant rate, has very few parts that can fail. The motion is slow, the force is minimal, and the wear on the components is almost negligible over time. This was engineering for permanence, not for planned replacement. The ancient aspiration was not for perpetual motion in the impossible physics sense, but for perpetual service, a machine that could outlive its creator and continue its work for generations to come. This drive to create enduring, self-sufficient machines reveals a deep-seated human desire to build a legacy that operates on its own, a spark of controlled autonomy that would flicker through the ages, waiting to be rekindled in a new era of invention. A gentle slope of stone and mortar carried life itself across entire landscapes. The Roman aqueducts were not just bridges for water, they were the vascular systems of an empire, engineered with a foresight that still delivers fresh water to cities 2,000 years later. This sustained utility was no accident. It was the product of masterful civil engineering designed for the very long term. At the heart of every aqueduct was a simple, unpowered principle: gravity flow. Roman engineers plotted courses over dozens of miles, ensuring a precise, consistent downward slope just steep enough to keep the water moving, but gentle enough to prevent destructive erosion. They used tools like the chorobates, a massive water level on legs, to achieve this exacting grade across valleys and hills. But the true secret to their immortality lay in the materials. They developed a revolutionary concrete using volcanic ash, known as pozzolana, which actually gained strength when exposed to water, curing into a rock-hard mass that could withstand the constant flow for centuries. These channels were more than just pipes, they were complete water management systems. They incorporated sedimentation tanks where water would slow down, allowing silt and debris to settle out before the cleaner liquid continued its journey. They built clever overflow channels and access points for maintenance, anticipating problems that might not arise for generations. The Aqua Virgo, an aqueduct completed during the reign of Augustus, still feeds the famous Trevi fountain in Rome today. Its continuous operation through the rise and fall of empires is a stunning testament to the original construction quality and the enduring value of the resource it provides. How did ancient planners design for such impossible longevity? They thought in terms of centuries, not years, building infrastructure not for themselves, but for a future they would never see. They understood that the most sustainable systems work in harmony with natural forces like gravity, rather than fighting them with constant energy input. This profound lesson in resilience, written in stone and flowing water, challenges our modern approach to urban utilities. It shows that true progress is not always about reinvention, but about building foundations so sound they can support civilization itself across the ages. This mastery of harnessing nature's own power extends beyond the flow of water to the very winds that shaped their voyages and the sands that measured their hours. The relentless turning of a water wheel or the slow sweep of a windmill sail represented a different kind of ancient endurance, one powered by the planet itself. These were not delicate instruments but robust engines of daily life, grinding grain and pumping water for centuries with a quiet, renewable rhythm. Across the globe, from the vertical windmills of Persia to the sophisticated water-powered trip hammers of China, these machines were masterclasses in sustainable design. Their longevity was woven into their very construction, using massive wooden gears carved from local timber and millstones of durable granite that could be resurfaced again and again, generation after generation. They were built not to be replaced but to be maintained, a continuous project for the entire community they served. Consider the Norse tide mills, wooden structures anchored along the coast that harnessed the predictable power of the ocean's tides. Some of these simple, brilliant designs operated for 500 years or more, their functionality uninterrupted by the rise and fall of kingdoms around them. Their secret was a profound integration with the environment, a harmony with natural cycles rather than a struggle against them. Why would a simple wooden mill outlast so many of our own complex technologies? The answer lies in a philosophy of adaptive resilience. A windmill's sails could be adjusted to catch the changing wind, and its entire upper section could be turned to face the breeze. A watermill's channel could be cleared of debris, its wooden components replaced over time without needing to dismantle the entire structure. This was technology as a living tradition, supported by locally sourced materials and the collective knowledge of the people it served. In our modern pursuit of green energy, these ancient mills offer a powerful lesson that the most enduring systems are often those that work with nature, are built from resilient, repairable parts, and are cared for by the communities that depend on them. This same principle of relentless, reliable operation would soon be captured in a far smaller device, one that measured not the power of nature, but the steady, unyielding passage of time itself. A shadow falls across a stone dial, its edge sharp and unwavering as it marks another passing hour. This was the unceasing measure of the sundial, a machine of pure geometry and light that required no fuel, no winding, and no intricate gears beyond its own perfect alignment with the heavens. From the great obelisks of Egypt that cast long timelines across palace courtyards to the portable bronze discs carried by Roman travelers, these devices turned the sun's daily arc into a universal clock. Their operation was elegantly passive, a silent collaboration between human craftsmanship and celestial motion. A master artisan would carefully carve hour lines based on precise calculations of latitude, ensuring the gnomon, the shadow-casting blade, was angled to match the tilt of the Earth's axis. This was not a rough approximation, it was applied astronomy rendered in enduring stone or metal. The Solarium Augusti in Rome was more than a monument, it was a public utility of time. A massive Egyptian obelisk served as its gnomon, casting a shadow across a vast marble pavement inscribed with a grid of lines that charted not only the hours but also the changing length of days throughout the year. Long after the reign of Augustus ended, this solar engine continued to function, its scale preserved in the resilient stone. Why did so many diverse cultures converge on this same solution for public timekeeping? The answer lies in its perfect blend of authority and accessibility. A sundial offered a single, unambiguous time standard for an entire community, synchronizing markets, legal proceedings, and religious rites under the open sky. Its longevity was guaranteed by the very forces it measured. The sun would rise and the shadow would follow, season after season, century after century. This quest for perpetual order, etched in stone, symbolizes a deep human desire to anchor our fleeting lives to the timeless rhythms of the cosmos. The silent, perfect geometry of the sundial represents one of humanity's earliest and most resilient computational tools, a machine that computes time using the sun itself as its processor. A merchant in ancient Rome slides polished pebbles across a grooved board, tallying a shipment of grain in moments. Half a world away, a scholar in Imperial China deftly moves beads on rods, performing calculations with a speed that rivals any written method. These were the abacuses and counting boards, computational engines that powered commerce and science for thousands of years, with some examples remaining perfectly functional today. Their design was a triumph of intuitive interaction, relying on human hands to move beads or tokens, a system that inherently avoided the mechanical where that dooms more complex machines. From the Mesopotamian dust to the markets of the Silk Road, these devices evolved into forms perfectly suited to their cultures, like the Roman calculi using stones on a lined table or the Chinese suanpan with its heaven and earth beads. Their parts were minimal and robust, typically crafted from durable wood, stone, or bone, with metal rods that could be straightened or replaced by any local craftsman. This was technology built not for a single lifetime, but for a civilization's duration. How could such a simple tool remain so vital across countless technological shifts? Mathematics historians point to its perfect alignment with the human mind, offering a tactile, visual representation of numbers that made abstract arithmetic concrete. The beads clicking into place provided immediate, error-resistant feedback, a physical logic that required no external power and could be mastered by anyone. An abacus found in an archaeological dig often shows remarkably little degradation. Its beads smoothed to a pleasant polish by generations of use, but its core function completely intact. This longevity speaks to a profound design principle that the most effective tools often have the fewest points of failure. They are not sealed away or made obsolete by minor improvements, but remain open, adaptable, and eternally repairable. In an age of digital fragility, the abacus stands as a quiet monument to computational resilience, a machine whose only moving part is the human hand. This same quest for reliable, long-term guidance would soon be cast in metal and glass, in instruments that dared to chart a course across the trackless sea. A polished brass disc, etched with a web of finely engraved lines, becomes a portable model of the night sky. Across deserts and oceans, astrolabes and early sextants offered timeless guidance, their accuracy preserved through centuries by masters of metalwork. Navigators would hold the astrolabe aloft, sighting a star or the sun through its pinwheels, the movable alidade rotating to reveal the celestial body's angle above the horizon. This single measurement, read against the intricate scales on the instrument's face, could pinpoint a ship's latitude or the precise time for an evening prayer. Each device was a masterpiece of calculation, its engraved plates, known as tympans, customized for specific latitudes, mapping the local heavens onto a flat, durable surface. The choice of materials was deliberate. Bronze resisted the corrosive salt air, while the careful balancing of the moving parts ensured smooth operation decade after decade. The Sloane astrolabe in the British Museum, crafted in the 16th century, remains a testament to this precision, its scales as legible today as they were 400 years ago. Why did such complex instruments become cherished heirlooms, passed from pilot to apprentice for generations? They were not merely tools, but repositories of essential knowledge, a physical library of the stars that guaranteed safe passage and spiritual order. An astrolabe from the Islamic Golden Age, for instance, could still accurately determine the Qibla, the direction to Mecca, or the 5 daily prayer times, its function unbroken by the passage of time. This enduring utility shaped the course of exploration and science, enabling voyages of discovery that connected continents and advanced our understanding of the world. The relentless pursuit of reliable, long-term guidance, cast in brass and glass, would soon inspire machines designed to bridge vast distances not with ships, but with words, transforming how humanity communicated across the ages. A single carved block of hardwood could produce 10,000 pages, each one a perfect copy of a sacred text or a royal decree. This was the quiet power of the early printing press, a machine for memory built from the most resilient materials available. Long before Gutenberg, Chinese and Korean artisans were perfecting systems of woodblock printing and movable type, using fired clay or bronze to create characters that resisted wear and decay. The process was elegantly straightforward. Ink was applied to the raised surface of the carved block or assembled type, and then pressed onto paper or silk. Yet the genius of this technology was not in its complexity, but in its profound durability. A masterfully carved woodblock made from seasoned pear or jujube wood could survive the pressure of thousands of impressions, its grooves remaining sharp and clear for centuries. The Gutenberg press, introduced in Europe in the 15th century, followed this same principle of robust simplicity. Its great screw and lever mechanism, crafted from iron and hardwood, was so fundamentally sound that its core design saw little need for change for over 300 years. The type itself was cast from a durable alloy of lead, tin, and antimony, a mixture that could be melted down and recast into new letters endlessly, creating a near-perpetual cycle of reuse. Historical records from Korea speak of vast sets of bronze type cast by royal decree, each character a small sculpture designed to be used and reused for generations of official publications. What allowed these machines to operate for so long with such minimal change? The answer lies in a perfect alignment of material and purpose. The presses were built from components that could be easily repaired or replaced by any skilled carpenter or metalworker, and the mechanism itself was so reliable that there was little incentive to reinvent it. This was not technology chasing novelty, but technology perfected for its core function, the faithful and endless reproduction of knowledge. We can see the result today in Buddhist sutras printed in 8th century Japan, their characters still crisp and legible on the page, a direct communication from the past made possible by a machine that refused to wear out. This relentless replication did more than just preserve texts. It standardized them, creating a stable foundation for culture and science to build upon. How did the perseverance of the printing press reshape the world? It broke the monopoly on information, allowing ideas to spread faster and farther than ever before, fueling revolutions in thought whose echoes we still feel today. The same drive to create unyielding, powerful machines would soon be applied to a very different domain, one where durability was not just about preservation, but about survival on the battlefield. A stone projectile weighing nearly 100 kilograms could be hurled against a fortress wall with relentless force, day after day for years. This was the brutal, enduring power of the ancient siege engine, a machine built not for delicate measurement but for raw, sustained impact. Far from being single-use weapons, these colossal devices were engineered for a long operational life, their robust frames and sophisticated tension systems allowing them to be deployed again and again across different conflicts. The most formidable of them all, the trebuchet, relied on the immense, predictable force of a falling counterweight. This gravity-powered design meant that the machine itself endured no internal strain beyond the shock of release, its massive timber frame absorbing the energy. After a day of bombardment, the counterweight could be winched back into position, ready to repeat its destructive arc. The Roman ballista, a giant crossbow that launched heavy bolts or stones, achieved its longevity through a different principle, torsion. Its power came from tightly wound skeins of rope, often horsehair or sinew, which stored incredible energy. The genius of its design lay in its modularity. Key components like the torsion bundles and firing arms were standardized and could be unbolted and replaced in the field, turning a damaged weapon back into a functional one with astonishing speed. Historical records indicate that some of these engines were stored in imperial armories for decades, only to be brought out, reassembled, and put to work in a new campaign a generation later. How did ancient armies maintain such complex machines during long periods of peace? They employed dedicated artisans, carpenters, and rope makers whose sole duty was the preservation of this military technology. The machines were often disassembled, with their wooden parts treated with tar or oil to prevent rot and their metal components greased against rust. This was a logistics chain built for permanence, an understanding that a well-maintained trebuchet was a strategic asset more valuable than a dozen new swords. Their longevity transformed them from mere tools of war into symbolic artifacts of imperial power. The legendary Helepolis, or Taker of Cities, was a 9-story siege tower used in the sieges of Rhodes and later, reportedly, in other campaigns. Its repeated use across years and battlefields speaks to a design so sound and a construction so resilient that it became a persistent legend. The enduring nature of these machines challenges our perception of ancient warfare as a crude affair, revealing instead a sophisticated culture of military engineering that thought in terms of decades, not just single battles. This same principle of building for generations, of creating tools meant to outlive their makers, would soon find a much quieter expression within the home, in domestic devices that served households for ages. The steady rhythm of a wooden shuttle flying back and forth created the cloth that clothed civilizations. Ancient looms and weaving frames were machines of quiet persistence, their wooden bones and simple mechanisms operating for centuries with a reliability that modern industry might envy. These were not fragile devices, but robust frames crafted from resilient woods like oak, elm, or bamboo, materials chosen for their strength and flexibility. The core design was a masterpiece of sustainable engineering, distributing the constant tension of the warp threads across the entire structure to prevent any single point from bearing unsustainable stress. This careful balance meant that the very act of weaving did not wear the loom out. Instead, the machine settled into a kind of durable harmony with its use. In ancient Peru, vertical looms produced intricate tapestries of stunning complexity, their vibrant colors and symbolic patterns telling stories that lasted for generations on a frame that itself endured. The weaver knew every part of her tool, and with a few simple implements, she could replace a worn heddle rod or tighten a loosened beam, performing maintenance that kept the essential machine alive. This is why weaving technology saw such beautifully incremental change. The core principle was so sound, so perfectly adapted to its purpose, that there was little need for revolutionary overhaul. Its longevity was a direct result of this evolutionary refinement, where each small improvement was tested across generations. The persistence of traditional handloom weaving in cultures around the world today is not merely a cultural artifact. It is a living demonstration of a technology that never truly became obsolete. It maintained its utility across millennia because it was accessible, repairable, and intimately connected to human skill. This profound relationship between a durable tool and the artisan who mastered it created a legacy of continuous service, a quiet hum of productivity that wove the very fabric of daily life. From the cloth that covered people to the sails that powered exploration, these enduring machines prepared the way for another class of tool, one that fed the world with the same seasonal reliability. The same iron-tipped plow that broke the soil for a Roman farmer could have been used by his descendant a dozen generations later, its form almost unchanged. These were not tools of convenience but instruments of survival, designed for a single, unending task to feed humanity season after season. The plow and its companions, the scythe and the threshing board, represent a class of machine whose endurance was forged in the fields, their longevity measured in harvest. Their strength came from a profound understanding of material and force, an iron share designed to slice through earth, its shape distributing the immense stress of pulling across a wide, resilient blade. The wood of the handle was not just a stick, but a carefully selected piece of ash or oak, chosen for its grain and ability to absorb the shock of striking a hidden stone without splintering. This was not high technology in the modern sense. It was perfected technology, refined over centuries into a form that could not be easily improved upon. The ard plough, a simple scratch plough used since the Bronze Age, is a stunning example of this principle. Its basic structure, a wooden frame with a metal tip, remained in continuous use for over 3,000 years. Its genius was not in complexity, but in its repairability. A worn share could be reforged by the village blacksmith, a cracked beam replaced with a new piece of timber, all without specialized knowledge or tools. This created a cycle of near-perpetual use, where the tool was not a single object but a continuous tradition of maintenance and renewal. Records from medieval manors show specific ploughs being passed down through families for centuries, their identity tied not to their original components, but to their enduring function. What cultural practices ensured this incredible preservation? The knowledge of how to maintain these tools was woven into the fabric of daily life, passed from parent to child as essential wisdom. A farmer knew that caring for his plough was as important as caring for his land, for this machine was the key to his family's future. This sustainable relationship with technology created a form of agriculture that was inherently resilient, built on tools that would not fail when they were needed most. The quiet, perennial function of the plough laid the literal groundwork for civilization itself, turning wild landscapes into stable, productive fields. This same principle of building for the ages, of creating machines meant to shape the very world around them, would soon be lifted to a monumental scale in the architectural engines that defined entire cities. A stone block weighing more than 20 tons swings slowly into the air, guided by nothing more than a wooden frame and a team of laborers pulling on ropes. This was the everyday reality of ancient construction, powered by cranes and lifting devices engineered for sustained, reliable operation. Far from being temporary contraptions, these machines were built to last, their principles of leverage and counterbalance allowing them to work on projects that span decades. The Greeks perfected the compound pulley, a system of multiple wheels that dramatically multiplied human strength, while Roman engineers deployed massive treadwheel cranes powered by men walking inside a giant wheel, converting their steps into immense lifting force. The true genius of these devices lay in their modular design. They were not single-use tools but reusable systems. Wooden frames, winch drums, and hemp rope assemblies could be disassembled at one building site, transported and reassembled at the next, their components serving for generations across an empire. Roman military records detail the systematic reuse of crane parts from Gaul to North Africa, a logistics network that treated these machines as valuable, long-term assets. How did they manage the immense risks of hoisting such colossal weights year after year? The answer was a relentless focus on maintenance and inspection. Hemp ropes, though strong, were susceptible to wear, so they were regularly examined for fraying and replaced long before they reached their breaking point. Wooden beams were chosen from resilient timber and designed with a safety margin far exceeding the expected load, a practice of cautious over-engineering that prevented catastrophic failure. This culture of careful use extended to the operators themselves, teams of skilled workers who knew the sounds and feel of a straining machine, able to detect a problem long before it became a disaster. The persistence of these fundamental crane designs is a story in itself. The very same principles that raised the columns of the Roman Pantheon were still in use 1,000 years later, hoisting the stone for the great Gothic cathedrals. This was not a lack of innovation, but a testament to a design so perfectly adapted to its purpose that it became timeless. The longevity of these lifting machines ensured that humanity's grandest architectural dreams could be physically realized stone by heavy stone. This mechanical resilience did more than just build structures. It enabled a different kind of enduring human achievement, one carved not in monumental stone, but in the far more delicate medium of sound. A potter's foot pushes rhythmically against a heavy stone disc, setting a lump of clay into a perfect spinning symmetry. This was the heartbeat of the pottery wheel, a machine whose timeless design revolved unchanged for millennia. Its core principle was the flywheel, a weighted disc that stored rotational energy, allowing the potter to maintain a smooth, constant speed with only gentle, periodic kicks. This elegant use of inertia meant the machine had almost nothing to break, its central pivot and stone bearing designed for a lifetime of friction and motion. Alongside it stood the kiln, a chamber of fire brick and clay that transformed soft earth into enduring ceramic. These were not separate tools but partners in a process of creation built for the very long term. The kiln's architecture was a masterclass in heat management, with flues and chambers designed to circulate intense temperatures evenly, preventing the thermal stress that could crack lesser structures. The materials themselves were the secret, often made from the very clays they fired, becoming only stronger with each use. Archaeologists have uncovered kilns in ancient Mesopotamia where the very walls are glazed with a glassy residue from countless firings, a testament to centuries of continuous operation. These structures were not discarded when a brick cracked. They were patched with a new layer of refractory clay, a continuous cycle of maintenance that kept the essential machine alive for generations. Why did this specific technology see such incredible longevity when so many other inventions came and went? The answer lies in its perfect alignment with human need. Pottery was civilization's essential container, used for storing grain, carrying water, cooking food, and honoring the departed. The reliability of the wheel and kiln guaranteed the stability of daily life itself. The slow, evolutionary improvements to their design were not about novelty, but about refining an already perfect process for even greater resilience. This created an unbroken thread of technical knowledge, where a master potter's skills and his well-maintained tools were passed down to his apprentices, preserving not just an object but an entire craft. The enduring hum of the pottery wheel and the persistent heat of the kiln did more than create vessels. They forged cultural continuity, allowing artistic styles and functional forms to persist across centuries. This relentless drive to create and preserve would soon find its ultimate expression in a machine designed not to shape clay, but to capture the human voice for all time. A simple bronze stylus, cool and solid in a scribe's hand, could etch the accounts of an empire onto a wax tablet, then be passed to his son, and his son after him, its point still sharp and true. These were the machines of memory, the humble style and quills whose relentless work preserved the voices of the past. Their design was a study in purposeful durability. A Roman stylus, typically iron or bronze, featured one pointed end for incising soft wax and a flat, broad end for smoothing mistakes and starting anew. This was not a disposable tool but a personal possession, its metal slowly wearing down over decades of use, yet remaining perfectly functional. The wax tablets themselves were brilliant in their renewable nature. The wooden frames protected the wax within, and when a message was no longer needed, the surface could be warmed, smoothed flat, and made ready to receive another dispatch, another contract, another piece of poetry. This cycle of writing and erasing, enabled by a tool that scarcely aged, created a sustainable system for daily record-keeping that lasted for centuries. How did such a straightforward technology facilitate the transmission of culture across generations? The answer lies in its accessibility and permanence. Scribes and scholars from Rome to Alexandria relied on these kits, their consistent design allowing knowledge to be recorded, edited, and carried across vast distances. The true testament to their endurance, however, is not just in the tools, but in the messages they left on harder surfaces. The Rosetta Stone, a slab of black granodiorite, bears inscriptions carved by chisels that have long since turned to dust. Yet the writing itself, the carefully struck hieroglyphs, Demotic script, and Greek characters, has remained perfectly legible for over 2,000 years. The stonecutters' tools, made of a metal harder than the rock they shaped, were designed for a single, monumental task: to create a record that would outlast kingdoms. This combination of resilient tools and resilient materials created a bridge across time, allowing us to directly read the words of people separated from us by millennia. The persistent memory held in these inscriptions did more than just record laws or royal decrees. It preserved the very structure of thought, the nuances of language, and the complexities of belief that defined entire civilizations. This drive to create enduring records reveals a profound human need to speak to the future, to ensure that a name, a story, or an idea would not be erased by the passage of years. The relentless, repeated action of a sharp point against a receptive surface, whether wax or stone, became one of history's most powerful engines, building a foundation of shared knowledge that all future progress would rely upon. This mastery of preserving thought would soon be paired with a different kind of ancient power, one that animated the largest machines of the classical world. A massive wooden wheel turns, its steps worn smooth by the feet of laborers walking in a perpetual circle. This was the ancient treadmill, a machine powered not by wind or water, but by the sustained rhythm of muscle. These human and animal-powered engines were the workhorses of the ancient and medieval worlds, converting the simple rotation of a wheel into the grinding of grain, the pumping of water, or the lifting of stone. Their genius lay in a sustainable cycle of power generation, a direct mechanical link between biological energy and useful work that could be maintained for centuries. The Roman treadwheel crane, for instance, used a team of men walking inside a giant wooden wheel to hoist massive blocks of stone, its robust gear train and stout timber frame distributing the immense load. Similarly, the animal-driven Norias of Persia harnessed oxen or donkeys to turn wheels that lifted water for irrigation, day after day, season after season. Their design was inherently durable. The moving parts were large, accessible, and built for easy maintenance. A worn wooden gear could be replaced by a village carpenter, a fraying rope swapped for a new one, and bearings lubricated with animal fat. This was not disposable technology. It was a community asset, maintained and repaired across generations. Engineering studies of surviving components reveal the subtle brilliance in their construction. The use of dense hardwoods for bearings provided a naturally low friction surface that wore down slowly, while strategic metal reinforcements at stress points prevented catastrophic failure under heavy loads. In the water-filled mines of medieval Europe, treadwheels made of oak and iron lifted buckets from astonishing depths for decades, their simple, reliable mechanics needing no technological updates. How did these machines achieve such a perfect balance of power and longevity? They were perfectly scaled to their energy source. The pace of an ox or a team of men provided a consistent, manageable force that did not overtax the machine's components, allowing for smooth, continuous operation that avoided the destructive jarring of sudden impact. This offers a profound lesson in sustainable energy use. These muscle-powered engines existed in a closed loop with their environment and their operators, a system where the fuel was food and the maintenance was a continuous, localized practice. They teach us that true sustainability is not just about the source of power, but about building machines that are repairable, understandable, and integrated into the community they serve. This relentless, rhythmic application of force, harnessed for generations, finds a parallel in another class of device, one that measured not the power of man, but the perfect motions of the cosmos with unwavering accuracy. A single plumb line hanging perfectly still in the desert night could define the axis of a pyramid for eternity. This was the flawless geometry of the Merkit, an ancient Egyptian sighting tool that turned starlight into architectural certainty. Priests and surveyors used pairs of these instruments, each a narrow, notched palm rib with a plumb line suspended from its end. By aligning the notch with a specific star as it crossed the meridian, they could establish true north with an accuracy that still baffles modern engineers. The sheer brilliance of the Merkit was its profound simplicity, a machine with no moving parts to wear out, no mechanism to fall out of calibration. Its only power was gravity, pulling the plumb bob into a perfect vertical, and its only components were durable wood and stone that resisted the passage of centuries. This was not a tool for a single project but a dynastic instrument, its reliable operation passed down through generations of master astronomers. The same principle of unwavering alignment was embodied in the Roman groma, a sturdy cross of wood armed with 4 hanging plumb lines used for surveying city grids and aqueduct courses. Its robust construction meant it could be used daily for decades, surviving the rough conditions of military campaigns and frontier construction, its precision undiminished. Why would ancient builders entrust the orientation of their most sacred and permanent structures to such seemingly simple devices? The answer lies in a culture of verification and cumulative knowledge. A Merkit's alignment was not a one-time guess. It was checked and rechecked over many nights, its reading confirmed against the consistent clockwork of the sky. The initial, painstaking calibration became a permanent reference, a true direction locked in by the stars themselves. The result of this relentless precision is written in stone across the globe. The Great Pyramid of Giza, aligned to the cardinal points with an error of less than 1/15 of a degree, stands as a silent witness to the Merkit's flawless service. Its sides have faced true north for nearly 5,000 years, a direct consequence of that first perfect observation. This architectural permanence, enabled by a tool that never tired and never drifted, shaped the very landscape of history. It created cities and temples that were harmoniously integrated with the cosmos, their enduring alignments a physical manifestation of a culture's deepest beliefs. The legacy of these unfailing alignment tools extended far beyond the foundation stones of temples. They laid the groundwork for a different kind of journey, one that required equally reliable machines to navigate the vast and trackless sea. The same adze that shaped the prow of a Viking longship could have been used by the builder's grandson to craft a trading vessel bound for distant shores. These were not disposable implements but heirlooms of the sea, tools forged from iron and hardwood with a singular purpose: to build ships capable of surviving the ocean's fury for decades. The shipwright's toolkit was a masterpiece of resilient design, each item crafted to endure the humid, salt-drenched environment of the shipyard. An adze handle carved from a single piece of seasoned ash, absorbed the shock of countless blows without splintering, while its iron head was thick and heavy, designed to be sharpened again and again over a lifetime of use. This was engineering for the very long term, where the tool itself became a repository of skill, its familiar weight and balance guiding the hand of each new generation. Historical records from Norse settlements speak of specific drills and hammers being passed down through families, their wooden handles worn smooth by generations of grip, yet their iron cores remaining perfectly sound. This continuity of craftsmanship was essential, for the durability of the tool directly enabled the durability of the vessel it built. A ship constructed with such care and such enduring instruments was itself a machine built for a long life, capable of crossing the North Sea season after season. This cycle of preservation, where a resilient tool built a resilient ship, created a foundation for epic voyages of exploration and trade. But a sturdy vessel was nothing without a way to guide it across the trackless blue expanse. The magnetic compass, a simple yet revolutionary device, provided that guidance for centuries without fail. Originating in ancient China, its design was a lesson in elegant permanence, a magnetized needle floating in a protective bowl of water or suspended on a low-friction pivot. With no intricate gears to jam and no delicate parts to break, the compass was remarkably resistant to the violent motions of a ship at sea. Its housing was often made of non-magnetic materials like wood or bronze to prevent interference, and its face was sealed against the corrosive salt air. This robust simplicity meant that a compass crafted in the 12th century could still point true north in the 16th, its faithful service enabling navigators to venture farther from familiar coastlines than ever before. How did the longevity of these tools reshape the world? They supported extended cultural exchange by making maritime travel a reliable, repeatable enterprise. A captain could plan a journey to a foreign port with confidence, knowing his ship was built with proven tools and his course was set by a device that would not fail him. The design principle behind their survival was a focus on serviceability and material truth. Tools were made from materials that could be maintained with basic skills: a dull blade sharpened, a worn handle replaced, a compass needle remagnetized. This created a technology that was not consumed but sustained, a perpetual engine of discovery whose components were as enduring as the human desire to explore. The relentless innovation of maritime technology, built on tools that refused to wear out, would soon find a powerful parallel on land, in the machines that transformed raw materials into the goods of daily life. The heart of a forge is a fire that never truly dies. For generations, the same anvil might ring with the hammer blows of a father, then his son, then his grandson, its iron face bearing the polished scars of countless creations. These metalworking centers were not just workshops, they were engines of civilization, built around machines designed for relentless service. The forge itself, often a simple hearth lined with heat-resistant firebrick, could withstand temperatures that would turn ordinary stone to slag. Its companion, the bellows, was a masterpiece of durable design, using leathers treated against cracking and wooden valves that sealed tight for decades, forcing a steady stream of air to feed the flames year after year. This was technology forged in fire, where every component was selected for its ability to endure extreme heat and physical impact. The anvil, a single block of wrought iron, was perhaps the most resilient machine of all. Its very form was a lesson in energy distribution, with a hardened face that resisted denting and a massive body that absorbed the shock of each hammer blow, protecting its own structure while shaping the metal upon it. Historians of metallurgy point to the Catalan forges of medieval Europe as stunning examples of this longevity. These efficient smelters used cleverly designed stone chimneys and air channels to create a continuous draft, allowing them to produce high-quality iron for 300 years or more with only minimal maintenance, like replacing the inner refractory lining. How did these tools achieve such extraordinary service life? Their secret was a perfect marriage of robust materials and modular design. A worn hammer handle could be swapped in minutes, a cracked firebrick could be pried out and reset, and the leather bellows could be restitched or patched without replacing the entire apparatus. This philosophy of repair, not replacement, meant the core machine could operate almost indefinitely. The persistence of these techniques in regions today is not a rejection of progress, but a testament to a system so fundamentally sound it never became obsolete. The unbroken operation of the forge underpinned every other technological leap, supplying the durable metal for plows, ships, and architectural tools. This relentless creation of essential goods from fire and iron finds a profound echo in a different kind of ancient workshop, one dedicated not to shaping metal, but to nurturing the human spirit. A hidden door swings open in a temple wall, moved by the heat of a sacred flame, and for 100 years it repeats this miracle every morning. This was the power of the ritual machine, a device engineered not for industry but for eternity. In sacred spaces across the ancient world, priests and engineers collaborated to build automated systems that performed ceremonies with a reliability that seemed divine. These were not mere decorations, they were functional components of worship, designed to operate for centuries with little more than occasional cleaning or a reset wait. The mechanisms were often elegantly simple, harnessing the steady drip of water to mark prayer times in an incense clock, or using a counterweight's slow descent to rotate a statue toward the rising sun each dawn. Their materials were chosen as much for their symbolic weight as their physical endurance, bronze for its connection to the gods and marble for its permanence. Historical records speak of the Parthenon's mechanical offerings, where a system of weights and pulleys, maintained by generations of priests, presented offerings to the goddess Athena on a precise schedule, day after day, year after year. The true genius of these devices lay in their cultural integration. Their operation was so seamlessly woven into the ritual that their mechanical nature became invisible, leaving only the awe-inspiring result. In some Hindu temples, water-driven altars have functioned for 1,000 years or more. A complex of stone channels and bronze valves regulates the flow of holy water, anointing a sacred idol in a perpetual, self-renewing ceremony. The flow rate is so precisely calibrated that it requires adjustment only once in a generation, a task passed down as sacred knowledge from master engineer to apprentice. Why would a society invest such immense resources into a machine that performed a single, repetitive ritual? The answer lies in the profound human need for constancy in the face of an uncertain world. A machine that never failed, that performed its duty through plagues and wars, was a tangible promise of order, a guarantee that the gods were still listening even when human hearts were filled with doubt. Its relentless operation reinforced tradition itself, making the ritual immutable and the passage of time itself a sacred, mechanical cycle. This drive to create perpetual ceremonial witnesses, machines that outlasted dynasties, would soon be directed toward a new frontier, not of faith but of fundamental discovery. A glass beaker, its sides marked with faded lines, could measure the same volume for 1,000 years. In the quiet of an ancient library or alchemist's workshop, such instruments were not passive objects but active partners in discovery, their unwavering accuracy allowing one generation to build directly upon the findings of the last. The precision balance, for instance, relied on carefully weighted bronze masses and a finely honed pivot point. Once calibrated, This tool could detect the slightest difference in weight for century after century, enabling reproducible experiments in pharmacology and metallurgy that formed a reliable foundation for early science. This was engineering for knowledge itself, where the machine's endurance guaranteed the integrity of the data it helped produce. Consider the simple yet profound water screw attributed to Archimedes, a hand-cranked spiral within a cylinder that could lift water with relentless efficiency. Its design was so mechanically sound and its construction so robust, often from waterproofed wood and corrosion-resistant bronze, that it remained in continuous use for irrigation and mine drainage from the Roman era straight through to the modern age. There was no need to reinvent it, only to maintain it, and in its persistent turning, it supported agriculture and industry across millennia. Even more delicate-seeming devices were built to last. Greek and Alexandrian scholars crafted complex burning mirrors from polished bronze, their parabolic curves so perfectly formed that they could focus sunlight to a pinpoint of intense heat. The same mirror, if cared for, could demonstrate the principles of optics for generations of students, its reflective surface never degrading, its experimental result always the same. This physical consistency was vital. It meant that a theory could be tested today with the same instrument used 100 years prior, creating an unbroken chain of verification. The legendary Lycurgus cup, a Roman glass cage cup from the 4th century, embodies this principle of lasting function. Its mysterious dichroic glass, which appears green in reflected light and a glowing red when light shines through it, is not merely a beautiful effect. It is a nanotechnological artifact, its properties created by embedded particles of gold and silver, so small and so stable that the cup still performs its stunning color shift 16 centuries later. It is both art and a permanent scientific demonstration, a captured light experiment that has never ceased. How did this incredible durability directly support the growth of knowledge? It prevented the loss of hard-won precision. A standard weight or measure, a reliably focused lens, a perfectly balanced scale. These tools became fixed points in a world of shifting theories. They were the shared reference that allowed different thinkers, separated by time and distance, to speak the same technical language and confirm each other's work. This created a slower but far more stable innovation cycle, where each advance was built on a bedrock of proven, repeatable results from tools that never betrayed their trust. The relentless pursuit of comfort then turned this same enduring ingenuity toward the machines that made daily life not just possible, but pleasant. A haunting melody could drift from a temple courtyard for 500 years, played by a machine with no musician in sight. These were the automatophones, self-playing musical instruments that turned engineering into enduring art. From the intricate water organs of ancient Greece to the mechanical choirs of the medieval Middle East, these devices were built to perform long after their creators had passed. Their operation relied on fundamental forces, a steady flow of water creating constant air pressure for a set of bronze pipes, or a heavy, slowly descending weight driving a pinned barrel that plucked a series of strings. This was music composed not just in notes, but in the very materials chosen, bronze for its pure, lasting resonance and hardwoods that aged into richer tonal qualities. The legendary hydraules, or water organ, invented by Ctesibius of Alexandria, is a prime example. Its brilliant pneumatic system used a column of water to regulate air pressure, providing a steady, unwavering stream of wind to its pipes. This design was so mechanically sound that it remained in use for over a millennium, from the games of the Roman circus to the sacred ceremonies of the Byzantine court. Its longevity was a direct result of its serviceable construction, where a worn leather bellows or a cracked pipe could be replaced without altering the soul of the instrument. Why would societies dedicate such resources to mechanical musicians? The answer lies in the universal human need for ritual and celebration. An organ that never missed a festival, a carillon that marked every hour without fail. These were more than conveniences. They were the audible heartbeat of a community, a guarantee of cultural continuity. The very same principle of preservation applied to handheld instruments. An Egyptian harp discovered in a tomb, its soundbox and armature still intact after 3,000 years, can have its ancient gut strings replaced and still produce a clear, ethereal tone. The acoustic principles understood by its maker, the precise ratios of string length to pitch, are as true today as they were then. This is not just durability, it is the immortality of an idea given physical form. The Chinese gyukan, a zither revered for its subtle and complex music, is another testament to this. Craftsmen used lacquered wood that cured and hardened over decades, the instrument's voice maturing and deepening with age, becoming more valuable with each passing generation. A master's gyukan was not merely owned, it was inherited, its very wood imbued with a sonic history. This relentless pursuit of lasting sound shaped our cultural heritage in profound ways. It allowed musical scales and compositions to be standardized and passed down with fidelity, creating a foundation upon which new music could be built. The enduring voice of these instruments connects us directly to the ears of the past, letting us hear an echo of the same melodies that once filled ancient halls. This timeless drive to create beauty that outlives its maker finds a parallel in a very different kind of machine, one designed not for pleasure, but for solving the most persistent practical problems of daily life. A heavy bronze key turns in a lock, and after 2,000 years, the bolt slides back with a solid, satisfying thud. This was the persistent reliability of ancient security, a machine built not for a single lifetime but for the safeguarding of generations. In the palaces of Egypt and the villas of Rome, intricate locking mechanisms secured everything from royal treasuries to family larders, their function a daily testament to enduring craftsmanship. These devices were marvels of practical engineering, employing principles like pin tumblers and warded keys that required precise, custom-made components to operate. A Roman key was not a simple shape, it was a unique signature, its projections designed to bypass internal obstructions called wards, lifting specific pins to a precise height so the bolt could be released. The materials were chosen with permanence in mind. Bronze and iron were forged to resist corrosion, and springs were tempered for resilience through thousands of cycles of locking and unlocking. The volcanic ash that buried Pompeii in 79 AD preserved a stunning time capsule of this technology. Roman door locks with their internal bolts and springs were found still in working order, their bronze components untouched by the centuries. The secret to their incredible longevity was a combination of robust simplicity and clever redundancy. The mechanisms had very few moving parts, and those parts were designed to withstand friction and wear. Security was not just about being impenetrable, it was about being reliably functional year after year, decade after decade. A lock that seized up or broke was a greater liability than no lock at all. This is why traditional blacksmiths in some parts of the world still produce locks using nearly identical designs, a direct lineage of knowledge and utility stretching back to antiquity. What design philosophy allowed a simple mechanical lock to protect resources so effectively for so long? It was a focus on perfecting a core interaction. The mechanism had to be complex enough to prevent casual intrusion, yet simple enough to operate flawlessly for generations with only basic maintenance, perhaps a drop of oil to keep the action smooth. This relentless dedication to durable security created a foundation of trust, allowing commerce to flourish and precious goods to be preserved through times of great uncertainty. The physical integrity of the lock was a promise, a small, steadfast engine of order in a chaotic world. This final class of machine, however, points to something deeper than mere mechanics. The most resilient devices often embodied the core values of the cultures that built them, becoming physical expressions of their beliefs about order, permanence, and the human relationship with the world. A gilded lion on a palace throne suddenly roared, a sound that echoed through the court not for years but for centuries. This was the power of the ceremonial machine, an engine of symbolism crafted to project authority and tradition far beyond the lifespan of any single ruler. These were not tools of war or agriculture, but instruments of state designed for one primary function: to impress and endure. Crafted from marble that defied weathering and bronze coated in gold leaf that caught the light of every new era, their physical resilience was a direct metaphor for the permanence of the institutions they represented. The legendary automated throne of the Byzantine emperors in Constantinople stands as a stunning example. Historical accounts describe a magnificent seat flanked by golden lions that would rise and roar on hydraulic or pneumatic systems during diplomatic receptions, a calculated display of technological majesty intended to awe foreign ambassadors. This was not a one-time spectacle, but a ritual performed for hundreds of years, its complex inner workings maintained by a dedicated guild of engineers whose sole task was to ensure the illusion of effortless, eternal power. Similarly, the Stone of Scone, an ancient symbol of Scottish monarchy, has been used in coronation ceremonies for nearly 800 years. Its longevity comes not from moving parts, but from its immutable presence, a simple block of sandstone that has witnessed the rise and fall of empires while remaining a central prop in the theater of kingship. Why would a society dedicate such immense resources to maintaining a machine whose only output was spectacle? The answer lies in the profound human need for continuity in the face of constant change. A roaring throne or an ancient coronation stone provided a tangible link to the past, a physical promise that the current ruler was part of an unbroken line, legitimized by tradition itself. Their maintenance was an act of political survival, a way for elites to demonstrate that their power was not fleeting, but as durable as the gilded bronze from which their symbols were made. This drive for symbolic permanence reveals a deep truth about our relationship with technology. The most resilient machines are often those that serve not just a practical need, but a profound psychological one: the desire to create something that can whisper the values of one generation directly into the ear of the next, long after the voices of its creators have fallen silent. A sword forged today in a Japanese workshop follows a rhythm unchanged for 800 years. The rhythmic strike of the hammer, the heat of the charcoal fire, and the shape of the anvil itself are all part of a living machine, a craft preserved not in a manual but in the muscle memory of generations. These traditional craft machines, from the Navajo weaver's loom to the master potter's wheel, are far more than tools. They are the engines of cultural continuity. Their incredible longevity springs from a powerful combination of community knowledge and adaptive design. While the core principles of the loom or the forge remain unshakably sound, small, thoughtful improvements are woven in over time: a slightly better shuttle design, a more efficient bellows. This slow, evolutionary refinement means the machine never becomes obsolete. It simply becomes more perfected, remaining perfectly relevant to the community it serves. Ethnographers point to the very tangible example of Japanese sword making, where specific forges have operated continuously for over 8 centuries. The tools themselves, the hammers and the water-powered trip hammers, are maintained and occasionally replaced, but the knowledge of how to use them, the precise angles and temperatures, is passed directly from master to apprentice through demonstration and shared experience. This is not just a transfer of skill, it is the transmission of a cultural identity. The persistence of the Navajo weaving loom demonstrates this profound resilience. The intricate patterns created on these sturdy wooden frames are a language telling stories of the people and their relationship to the land. The loom itself, often handed down through maternal lines, becomes a physical anchor for these stories. Its continued operation a quiet act of cultural preservation in the face of sweeping modernization. How do these machines facilitate such deep intergenerational learning? They create a hands-on classroom where failure is a lesson and success is a shared achievement. A young apprentice does not just watch, they feel the resistance of the clay on the wheel or the tension of the warp threads, learning a knowledge that is felt as much as it is understood. This offers a transformative lesson for our own approach to technology. In a world of planned obsolescence, the enduring craft machine teaches us that sustainable technology is not necessarily about the newest innovation, but about perfecting a system that is repairable, understandable, and deeply valued by the people who use it. It shows that the most resilient systems are those woven into the very fabric of community, where the machine's longevity is a direct reflection of the culture's determination to endure. The quiet hum of a modern server farm and the steady drip of an ancient water clock are both measures of human progress, yet one is built for replacement and the other for permanence. Our journey through these timeless machines reveals a profound truth, that longevity is not an accident of history, but a deliberate achievement. From the cosmic calculator of Antikythera to the community loom, these devices shared a common philosophy. They were constructed from resilient, locally sourced materials, designed for easy repair by the people who used them, and engineered to work in harmony with natural forces like gravity, water flow, and sunlight. This was not primitive technology, it was perfected technology, refined over generations into a form that served a core human need with unwavering reliability. The true mystery is not how they lasted, but why we ever moved away from building things to last. These ancient innovators thought in terms of centuries, embedding their values of stability and continuity into the very gears and stones of their creations. They understood